This is the summary of the topic complex envelope. So in the previous session we studied what is pre-envelope and how to extract the pre-envelope for positive frequency and the negative frequency. So pre-envelope is a complex signal in which imaginary part is Hilbert transform of real part. So if this is our low pass signal, its frequency spectrum is as shown. So it can be represented like this. That is nothing but frequency spectrum of positive pre-envelope and frequency spectrum for negative pre-envelope. So these two are the expression equation 6 and equation 10. So now we are going to proceed further to understand complex envelope. So complex envelope of bandpass signal. So let us consider bandpass signal S of t whose Fourier transform is exist. Therefore, we have written this expression. So the amplitude spectrum of S of t is as shown. So here we are able to see the carrier frequency Fc, and here W stands for the bandwidth. So here we are able to see the bandwidth is much lesser than the carrier frequency. Therefore, this bandpass signal is considered as narrow bandpass signal. So complex envelope for this narrow band signal S of t is given by S tilde of t, that is nothing but pre-envelope multiplied by exponential of minus j2 pi fct. What is S tilde of t on left hand side? It is complex envelope of band pass signal, that is given by what is S plus of t plus stands for pre-envelope of this band pass signal. So this equation 1 relates complex envelope S tilde of t of this band pass signal S of t with pre-envelope of the band pass signal S of t. So now we are going to use the frequency shifting property of Fourier transform in order to understand complex envelope. So here applying Fourier transform frequency shifting property on equation 1, that is this equation 1 here. So we are going to get in frequency domain S tilde of f, that is equal to S plus of f plus fc. So this is our second equation. So let us write the amplitude spectrum of S plus of t for this. So here we are able to see the spectrum of this S plus of t is limited to this frequency, that is fc is greater than fc minus w less than equal to fc plus w. Again, we are going to apply frequency shift property of Fourier transform on this signal. So we are going to get the amplitude spectrum of the complex envelope of the signal, that is as shown here. So this figure shows that amplitude spectrum of complex envelope S tilde of t of S of t. So what it indicates here, the complex envelope is centered at f is equal to 0 with frequency greater than equal to minus w less than equal to w. And here the complex envelope S tilde of t of a band pass signal is complex low pass signal. So I repeat, complex envelope S tilde of band pass signal S of t is complex low pass signal. Whatever the information content of band pass signal is preserved in this complex envelope. So now let us try to solve some problem on this complex envelope. So the statement will be like this: find pre-envelope, complex envelope, in phase and quadrature phase component for AM signal. S of t is equal to m of t cos 2 pi fct plus phi. So m of t is nothing but low frequency signal, and this is the carrier signal. So by the property of Hilbert transform, we can use this property. Hilbert transform of m of t c of t is given by m of t into Hilbert transform of c of t. M of t is a low frequency signal, c of t is a high frequency signal. So what is the expression for pre-envelope of S of t? That is given by, here pre-envelope from our previous discussion, it is given by S plus of t is nothing but a complex number. It is represented by the equation 1, real part S of t plus Hilbert transform of real part is the imaginary part. So now S of t is given, find its Hilbert transform. So S plus of t is equal to, S of t is nothing but m of t cos 2 pi fct plus phi plus j into, here apply Hilbert transform properties. M of t is low frequency signal, Hilbert transform of cos 2 pi fct plus phi. So Hilbert transform of cos 2 pi fct plus phi is nothing but sin 2 pi fct plus phi. Therefore, you can reduce this equation in exponential form like this. The pre-envelope of the signal S of t is given by m of t into cos 2 pi fct plus phi plus j sin 2 pi fct plus phi is represented in exponential form as in equation 2. So how to find complex envelope? So from our previous discussion, we know that complex envelope of a band pass signal, that is given by positive pre-envelope multiplied by exponential minus j2 pi fct. So this will be our equation 3. Now substitute equation 2 in equation 3. So reduce this. Complex envelope of band pass signal S of t, that is given by m of t e to the power of j 2 pi fct plus phi. This is nothing but our positive pre-envelope, multiply it by exponential minus j2 pi fct. Simplify. So here this term and this term get cancelled. We'll going to get m of t into e to the power of j phi. Now we have to find in phase and quadrature component of this complex envelope. So from our previous slide, complex envelope of band pass signal is given by m of t e to the power of j phi. What is e to the power of j phi? It is cos j phi plus j sin phi. So substitute and write here and identify in phase and quadrature phase component. In a similar way, solve the problems as shown here. Here you have to find the pre-envelope, complex envelope, and then in phase and quadrature component for PM and SSB signal. S of t is equal to cos 2 pi fct plus phi of t, first problem. Second one is S of t is equal to AC by 2m of t cos 2 pi fct plus AC by 2m cap of t sin 2 pi fct. Here m of t, m cap of t are low pass signal, whereas cos 2 pi fct, sin 2 pi fct are high pass signal. So use Hilbert transform property and obtain the solution.